Hello, this is Calculus 1, Lecture 12A, Optimization, Part 2. My name is Scott Grizzard from the University of South Florida. So last time we talked about optimization, and we had this idea that what we had to do was take two equations and find one equation with one unknown. So we had to combine the equations, and then what we had to do was we had to work it sort of like a related rates problem in that we figured out what was going on. We made one equation from the two. And then what we did was we found the maximum or minimum, whatever we were trying to optimize. And then we did something to check to make sure that we had what we were looking for, that we had the min or the max. So we either did the first derivative test or second derivative test or talked about the endpoints, one of those three things. So what we want to do today is continue this argument, but look at it from a slightly more sophisticated perspective. Now, you can get away if all you're interested in is passing the test and being done with it, and Calc 1's the end-all be-all of your mathematics, then you can get away with only the information from last lecture. And let's review how that went very quickly. So let's say the Acme Corporation produces explosive tennis balls, and I have some production function that looks like that. Labor costs $15 an hour. Rent on capital costs $30 an hour. What's the least expensive way of producing 2,000 boxes of explosive tennis balls? So I have my output, my capital, my labor, my cost, and all of these little fun things that we had last time. We minimize the cost subject to this quantity, which is fixed. And what we're going to do is build one equation with only one unknown. So we combine the two equations. We solve for capital here. And then we throw in this k for this k right here. I'm sorry, we throw in this k for this k right here. And then we come up with one equation in terms of L. And then we just took the derivative, set it equal to 0, and we found the L. We use that to find the k. And then we find the total cost to produce those units. And then we needed some way to verify that we had a minimum. And in this case, I just did a first derivative test because I didn't feel like taking a second derivative of this thing. I could have done that as well. And what I would have found is that I was decreasing, then increasing, so I had a min there. And then I said something about it. I restated my the end. Okay, so that's one way to do it. There's another way to do it, and it's more like a related rates problem in the way that you approach it. And the insight is that it doesn't matter which one is minimized or maximized and which one is fixed, because either way, the derivative is going to equal 0. So the derivative of cost with respect to L needed to equal 0 because we're minimizing, while the derivative of quantity with respect to L would have been 0 because Q is fixed. But if I was maximizing Q for a particular cost, then this would have been 0 because it was fixed, and this would have been 0 because it's optimized. So either way, we're going to wind up with 0. So there's another way to solve this, and this is in your book. It's called something like it's under one of the examples, and it's called Method 2. So let's talk about this Method 2. How would I do this? Well, I'm going to ignore this. And I'm going to look at this right here, and I'm going to ignore this 2,000. I'm going to look at this, this, and this. So this one's fixed. This one I want to optimize. Now, I'm going to pick one of these to be the driver. Since I used L before, I'm going to pick it. I'm going to pick L. And then I've got two equations here. I've still got Q. I've still got that, but I also have C equals. All right, so I've still got these two equations, but instead of solving one of them for the other variable, I'm just going to take the derivative of everything. So I'm taking the derivative of Q with respect to L. I'm going to have a product rule there. Now when I solve it, I'm going to have a chain on this one. This is a bit more like a related rates problem again. But now I'm going to set this equal to 0 because Q is fixed. But notice it didn't actually matter which one was fixed and which one was optimized. I'm just going to set both equal to 0. So I'm going to move this one over to the other side of the equation. You know what? I'm just going to solve for dk over dl here. So the 1/2 will go away. That -1 still hangs around. So I have negative, I'm going to solve for this thing right here, dk over dl. This I'm going to move over to this side, so this is going to go on the bottom. To the 1, so this will be over L, and then I'm going to divide both sides by this L to the 1/2, so I'm going to get a whole L over here. And then this k to the -1/2, I'm going to just solve. I'm just going to multiply over by the square root of k on both sides, and I'm going to wind up with that. So what this says is that when I'm optimized, the derivative with respect to of k with respect to L will equal -k over L. Well, how does that help me? Well, let's take the derivative of the cost function. And I do a little sum roll. And then I have a chain right here. So now I have dc over dl is going to equal this. But remember that dc over dl equals 0 because I'm optimizing. So the 15 is going to come over here. So now I have that dk over dl is going to equal -1/2 when I optimize. Why do I do this? Well, it offers a little bit of insight here. The first bit of insight is it separates the things that are moving. It in one sense separates the cost and the quantity equations, the output and the cost equations, and kind of gives you what's affecting what here in the optimum. It also lets me set an ideal ratio for k over L. So I set this equation, I set dk over dl from this equation equal to the one from that equation, and I get the following. So I take these two things and I get that negative. So that gives me an optimal ratio. Now, as we recall from last time, right here we got an optimal ratio when we're doing the rectangle. Because the costs were equal, we wound up with an optimal ratio of 1:1. Okay, that length would equal width. And if we had fiddled with these numbers, right? If I had made this twice, if I had made width 20 per feet, while length was 10 per feet, I would have wound up with an optimal ratio of 2:1. Okay. So that's interesting. It lets you solve for an optimal ratio. And notice that ratio, it doesn't matter whether I'm maximizing the production or I'm minimizing the cost. That's just the optimal ratio of the inputs. So it doesn't really matter which was done. If I was maximizing cost, if I was minimizing costs or maximizing output, it doesn't matter. I'm still going to wind up with the same optimal ratio. So that's the first insight, that these two problems are dual to each other. The next big insight, well, that's one of the big conclusions, not really one of the big insights. Okay, so the next thing that's going on here, I'm going to take this optimal ratio, and now I look at what I'm maximizing. So my optimal ratio here was k over L was 1/2. So now I'm going to plug this back in to the one that's fixed. It's 2,000 is the one that's fixed. Okay, and now I'm going to take k over L equals 1/2. That means that k equals 1/2 L, or L equals, all right, I've got k equals 1/2 L, or L equals 2k. So I could substitute either one of those in. So now I get that k equals 2,000 over √2. And so that means that L, and then I wind up with L equals 4,000 over √2. If I multiply by √2 over 2, I wind up with √2 times 2,000, because this will become a 2 on the bottom, and that'll cancel that 2. And that's the exact same numbers I got before. Okay, now I have to make an argument that I minimized. Okay, well, I could still do a first derivative test. It looked messy, but I could. Or I could just make an endpoint argument. So here I'm making just a simple input argument that if I take k to 0, my costs go to infinity, and if I take L to 0, my costs also go to infinity. Okay, so that's how you do this. All I've done is I did the exact same thing. This is kind of the end. I just made an endpoint argument. And so what I did was I took the derivative of both, set them equal to 0. Okay, so that's the method. There's another insight in here, is that it allows me to solve for what's called the expansion path. Okay, so the expansion path is what happens as I expand. What I want is a function. I want Q as a function of C, or vice versa. Okay, so I want a relationship between the output and the cost if I optimized. Okay, so that's going to tell me what goes on as I expand, hence the word name expansion path. Okay, so how do I do that? Well, I know what C was, and I have Q. Okay, and I also know that when optimized, okay, so I know what's going to happen here when I take the derivative, set it equal to 0, and optimize. I know that I'm going to wind up with L equal 2K. So now what I'm going to do is I want a relationship between C and Q. Okay, so that's what I'm going to do. So I've got Q. When optimized, Q is going to equal K to the 1/2 times 2K to the 1/2, which is from this equation, and that, which implies Q equals the square root of 2 times K. Okay, so I know that's always true. Okay, when I'm optimized, this is always going to be, the Q is always going to be the square root of 2 times K. So now I've gotten rid of L in one of my equations. Likewise, C, I'm going to take L here and I'm going to sub it in here. So this L equals 2K implies both of these things. So I just took 2K and I sub it in for L up here. Okay, so I know that my cost is going to be 60K. Now I'm going to take this information, I'm going to plug it in here. So I take Q, and that is my expansion path. So what I've done is I've subbed in, I've taken my optimization ratio here, my L equals 2K, and I plug that both back into C and K. Okay, so I plugged both of those into L for both C and K, and that got me one variable, right? Excuse me. That got me both equations in terms of K, in terms of one of the variables. Then what I did was I took the K, those two equations, and I combined them into a relationship between Q and C. Okay. And that's called the expansion path. Well, the expansion path tells me how this is going to grow, and it tells me that I have constant returns to scale. Okay? So if you give me, this says, so if I had $600 and I was making the simoleons, and I was making the explosive tennis balls, this would tell me for $600 I could make square root of 2 times 10 of them. Okay. It also tells me about what goes on with this thing, because I know that the derivative of the expansion path is interesting. And then I know that I have constant returns of scale because the second derivative of this equals 0. And that's rather interesting. Okay, so now I'm able to solve for the expansion path, which will give me an equation that will tell me when optimized, how much output I produce for a certain amount of money. And then I also know something about the production. In this case, I have constant returns to scale. So it doesn't matter how much more I want to produce. The marginal cost is always square root of 2 over 60. Okay, that's interesting. If you want to know more about this, take an econ class. I would highly suggest. This will let you math through a little bit of your econ, which is nice. Speaking of mathing through econ, okay, let's do one more example of optimization. So why do I set marginal cost equal to marginal revenue? Well, profit equals revenue minus cost. Okay, the traditional thing for this is to use a giant pi. Okay, this is a capital pi. That pi is not the number, it stands for profit. Because they want to reserve P for price, they use pi, big pi for profit. Okay, so, and again, it's not the number pi, it's just a variable. It's just what they use for the variable, a capital pi. And it should be noted that all of these are functions of Q. Now, since I'm maximizing, I'm going to take the profit and I'm going to set it equal to 0. Okay? Thus, I just saved you an entire econ lecture, right? It usually takes economists, your micro professor was going to take about an hour to build up to this. And he's not going to say it as cleanly as this. This I said in about 5 minutes. You've now proved that when I maximize profit, I set marginal cost equal to marginal revenue. There you go. So you math through some of your econ lectures. Okay, so what we did today was we emphasized this idea. Remember, our big idea was that I can set both just equal to 0. And that gave me this idea that these problems, maximizing the output or minimizing the cost, are dual to each other. Because if I'm maximizing output, I'm going to set it equal to 0, and I'm going to have some cost, which are fixed. So the derivative of the cost is simply going to be 0. Likewise, if I'm minimizing cost, I'm going to set the derivative to 0 because I'm minimizing, but then I'll have some fixed output. So that derivative is 0 anyway because it's fixed. So that was the idea. I'm setting both to 0 no matter what I do. So I just set them both equal to 0, and then I solve for one of the derivatives. I solve for the dk over dl or dl over dk, depending on which one I chose as the driver, and I wind up with an optimal ratio. And then what I can do is I can sub that optimal ratio back in to the things, and I find, and I could solve for the problem in my particular case, but in more general, I could solve for an expansion path and get a function in a general case, so that I now have a function of cost of quantity relating output. Okay, next time, don't forget that there's a test at the end of week 12. And next time, what we're going to do is we're going to talk about area under the curve and the area under the curve function. Okay, so that's what I have for you. Goodbye, and I'll talk to you later.